Hello viewers, in this lecture I will be covering performance improvement of CPU by pipelining technique. Pipelining technique can be understood clearly if I take one real life example first. This is a laundry room example. In a laundry room there is a washer, there is a dryer and a folding table. Washing takes 30 minutes, drying takes 40 minutes, and folding the clothes takes 20 minutes. So, total laundry operation will take 30 plus 40 plus 20, 90 minutes of time. Now, if there are four people, they have to wash, dry, and fold their clothes. And if they are not doing the pipelining technique, then the second load is starting after 90 minutes, and then the third load is starting after 180 minutes, and like that. So, four loads will take 90 into 4, 360 minutes or 6 hours. But as the washing machine and the drying machine are separate, there is no need to wait. When the first load is in the dryer, second load can use the washing machine. But because the washing time and drying time little different by 10 minutes, then second load, even after washing the clothes, it has to wait for 10 minutes to get the dryer. Okay, so total four loads will take here 3.5 hours. So previously four loads was taking 6 hours, and here it is 3.5 hours. And so the speed up is 6 hours by 3.5 hours is 1.714 times. So it is the same concept that can be applied for instruction execution also. We have seen that instructions have different stages. It can be divided into different stages. We have seen before this diagram that there is a instruction fetch operation, then instruction operation decoding, then operand address calculation, operand fetch, operand data operation, operand address calculation, operand store, interrupt checking, etc. etc. And then the instruction fetch for the next instruction happens. Because these stages are separate, they can be made completely separate from each other so that they don't depend on each other. And we can apply the pipelining concept. In this picture, it is showing, in the top picture, it is showing if pipelining is not implemented, and if the entire instruction is getting executed in the CPU, and then only the second instruction is starting, then let's see how much time it will take. Now each instruction is showing divided into four stages, and instruction fetch is taking 2 nanoseconds of time, and register read is taking 1 nanosecond, ALU is taking 2. So all these stages are taking different amount of time, but total instruction execution is taking 8 nanoseconds of time. I'm just saying nanosecond because that is an usual time that takes. The unit is not mentioned here. So, two instructions will get executed in completed in 16 nanoseconds, and three instructions will get completed in 24 nanoseconds without applying the pipelining technique. Now, the bottom picture is showing that if all the stages are made equal. So if reading from register was taking 1 nanosecond, then it is made to read take 2 nanoseconds now. So In that case, individual instruction execution is taking 10 nanosecond, and with pipelining approach, three instructions will get executed in 14 nanosecond. So here the speed up that can be achieved is 24 nanosecond divided by 14 nanosecond, 1.714 times performance improvement. Okay, so that is the idea. So let's see what we have to keep in mind for pipelining. Pipelining does not reduce latency of a single task. We have seen that previously it was taking, without pipelining it was taking 8 nanosecond, with pipelining it was taking 10 nanosecond, because now the all the stages are made equal. So latency or execution time of individual instruction is not decreasing, but the benefit is coming from the throughput of the entire workload per second. How many instruction that we have seen how much speed up. Now actually in a pipeline the potential speed up equal to number of pipelining stages. So we haven't seen that number. We have seen 5 stage pipeline, but the speed up was not 5 times, it was around 1.714 times. So why less? This is because there was unbalanced length of pipeline stages. We made all of the stages of 2 nanosecond time. So there the latency also increased a little bit. And there is another problem which is called pipeline filling and pipeline draining time wastage. Okay, so let's see the pipeline draining and pipeline filling time wastage with a bigger example. So now we are going to see a pipeline which is divided into 6 stages. Instruction fetch, decode instruction, calculate operands or effective address, fetch operands, execute instruction, and write result. These are the 6 stages. And we are going to see a big example with a 9 instruction now. So one instruction takes 6 cycles, and if without pipeline, this 9 instruction will take 6 times 9, 54 cycles. But if pipelining is there, then they are getting completed in 14 cycles. So the speed up is 54 by 14 for 9 instruction. Actually, if we take a bigger example of 1,000 instructions, then we can the speed up will improve. You can see uh, the speed up will be for 1,000 instruction without pipelining is 6,000 cycles, and with pipelining it will be 1,005 cycles, and speed up will be 5.9 times. Even though the maximum potential of the pipeline is 6, but it is 5.9, very close to 6, and much better than the small example we have taken with 9 instruction. So why it is not completely 6, that we will see here, and that is because of pipeline filling and pipeline draining time wastage. Here you can see in the first cycle only one stage is working, fetch instruction. Second cycles 2 stages working. Third cycle 3. But from 1 to 5, not all stages are working, and it is called the pipeline filling timer stage, which is slowing down the speed up. And only on 6, 7, 8, 9 cycle, all stages are working, all 6 stages are working. So that is the maximum utilization of the pipeline. But from 10 to 14 again, you can see less number of stages are working, and in 14 cycle only one stage is working, and that is called the pipeline draining time wastage. And this is because of these two time wastage, speed up is not reaching maximum potential. If we take bigger example, 10,000 example, 10,000 instruction, it will be very close to 6. But actually in a pipeline, there are many other kind of hazards or problems are there. And those are called pipeline hazards. And there are mainly three types: structural hazard, control hazard, and data hazard. We are going to see what is structural hazard. When same stage is needed by two different instruction at the same time. And we will take the example of memory. You know that in the memory, data is also there, instruction is also there. Now if the data access and instruction access are required at the same time, instruction access is required in the instruction fetch stage and data access is required in the mem stage. And if they are this same access is required by two different instruction at the same time, that may not be possible. If the memory is single ported, then there is only one read and one write. But if two reads are required, that will not be possible. And that gives structural hazard. But this structural hazard can be avoided by improving the hardware. Make the memory double ported so that two reads are possible at the same time. So that is one solution. Now, second kind of hazard is called data hazard. Here it is showing two instruction. One is called increment instruction, increment r1, and second instruction is add r2 comma r1. Now you can see r1 is the common register between the two instructions, and second r1 must happen after the first instruction is done. Otherwise, the logical meaning of the program will not be the same. So second instruction has to wait till the first instruction is completed, and that is called data hazard. Actually, there are many three different kinds of data hazards. So there we are going to see, and most of the time these data hazards can also be improved by improving the pipeline hardware. We are going to see that soon. And in one case, it cannot be avoided. Hazard cannot be avoided. We are going to see that case also. And the third one is called the control hazard. You know, when the instructions are executed, the program counter register automatically increment by one and next instruction is fetched. But if the previous instruction is a branch instruction, then it can branch to different portion of the program. So the instruction that has been already fetched, that will not be operated on. A new instruction need to be fetched, and that is called control hazard, and that also slows down the pipeline, and we are going to see those examples also. So here some definition is given again why the maximum speed up is so hard in a pipeline. Three hazards are there. First one is called structural hazard. Different instruction at different stages in the pipeline want to use the same hardware resource. Like I gave the example of the memory, primary memory access. It can also be the register file in the CPU. All the registers in the CPU are grouped together and is called the register file. If that is also not double ported, to read simultaneous read will not be possible. And then the second hazard, control hazard, succeeding instruction to put into pipeline depends on the outcome of a previous branch instruction already in pipeline. And third one is called data hazard. An instruction in the pipeline requires data to be computed by a previous instruction still in the pipeline. Now we see the pipeline data path. One example here for structural hazard. So here it is showing a small program of four instruction. All of them are load instruction. LW stands for load word. $1, it is another name for registers. $1, $2, these are the register names. So load word $1, comma 100 with inside parenthesis $0. This is an assembly language instruction, assembly code. And here you can see the five stages of the pipeline is instruction fetch, then register read, then ALU, then data access, and then again register write. So instruction fetch will fetch this instruction, then register read because it has to bring $1 and $0. These are the name of register from register files. Then ALU will compute this 100 parenthesis $0. This is one way of addressing mode. So whatever is in $0, it will add 100 with that. That will happen here. Then it will this 100 within parenthesis $0 is actually the address of the data. So now it will go for data access from main memory, and after accessing it will put the data into $1. So the meaning of this instruction is go to this address $0 plus 100 in memory, bring whatever they are and put it in $1. So data access is happening here. Now let's look at the fourth instruction, that is also a load instruction, $4 comma 400 comma $0. So here instruction fetch is happening between 5 to 8, 6 to 8 nanosecond, where for first instruction data access was happening. One was for data access, another was for instruction fetch, and that is an example of structural hazard. If the memory is single ported, it will not be possible. But if the hardware is improved to double port memory, then this structural hazard can be avoided. And basically, in modern computers, all structural hazards are easily avoided by improving the hardware. And it is saying MIPS was designed. MIPS is an architecture. It stands for one computer architecture instruction set. It is not million instruction per second, which you have read before about the throughput metric. It is a computer architecture which is based on reduced instruction set computer RISC architecture. And all this instruction that you are seeing there, this is the format of the MIPS instruction set architecture. So it is saying in MIPS is designed in such a way that all structural hazards are avoided. Now see the different data hazards nomenclature and what is the problem. So first kind of data hazard is called read after write or raw hazard. Here you are seeing two instruction add R1 comma R2 plus R3. It means add R2 plus R3 and keep the result in R1. Similarly for second instruction add R1 with R5 and keep the result in R4. Now you can see these two instruction has common register R1 and there is a data dependency is there. Second instruction must read R1 after the first instruction has written it in R1. And this is called data hazard, and this kind of hazard is called raw hazard or read after write. The second instruction must read after the first one has written. And this kind of hazard can also be avoided by improving the hardware by a technique called forwarding or bypassing. We are going to see that. But in one particular case, it cannot be avoided. That example also we are going to see. Now, second category of data hazard is called write after read or word hazard. Here also an example of two instruction. Here you can see R2 is the common register between the two instruction, and second instruction must write the result in R2 after the first instruction has read its value from R2. And this is called write after read hazard. Actually, this is not a problem because the pipelines have many stages, 5 stage, 6 stage. Actually, in practice, it is very long. Pipeline stages are 20 stages or 25 stages. And because read happens much earlier than write, reach stage is much earlier than the write stage, this problem doesn't happen. This is just a theoretical case. Then the third hazard is called write after write or wow hazard. Here you can see R1 is the common register between the two instructions, and both the instructions are writing in R1. So second writing should happen after the first writing has happened. Otherwise the meaning of the program will be different, and most of the time it is not a problem because second instruction will write after one clock cycle than first. But to avoid many hazard, compiler takes some technique called instruction reorganization or reshuffling, and that time computer must keep a note of this problem so that the order of writing in the register is maintained. Now let's see that raw hazard, which I said that can be avoided by bypassing or forwarding hardware. Here it is showing the example of raw hazard. First instruction will be writing back R2 plus R3 will be written back after the fifth cycle in write back cycle, and second instruction need it in the third cycle. So it has to wait 3 cycles and then it can decode the instruction here. Okay, and if the second instruction is stalling for some cycle, the other cycles next to it also need to stall. So this is called pipeline stalling. This example is clear. The blackened out stages are the stall, but it can be avoided by bypassing technique that I'm going to show you here. Here you can see this is a pipeline hardware is shown. This is the instruction fetch. The square box is the memory. Memory keeps instruction data both. Instruction fetch is accessing memory. Then register fetch because uh, it has to register $1 $0, then it will be executed here. So first instruction is producing the result here, and then it will write back here, but don't wait that long. As soon as the result is ready, bypass it here, and if that can be done, then raw hazard can be avoided, and in that particular case it was avoided. Now let's see a little bit bigger problem with 5 instruction. Between first and second instruction itself there is a raw hazard, and this R1 will be R2 plus R3 is happening here in the execution stage. If that result is forwarded here, then the second instruction don't have to stall, and this is called bypassing or forwarding. It can be, if it is bypassed from here, no wait at all. Now third instruction also had a data dependency with the first instruction, but here it was needing it here. So in memory stage, it can be forwarded, or it can be forwarded from the here to here also. And if that is done, there is no stalling in the pipeline. And the technique that is taken is called data forwarding. Okay, I think I will stop here because I have few more things to cover, other kind of hazards and the kind of raw hazard that cannot be avoided, the load use hazard. And but it will take some time. This video will be longer. So I'll be continue with another video for all the remaining concept of the pipeline.